can do is we can go ahead and pull the area out of these terms. So I'm going to have the area sitting out front here. Okay. The volume here is the area times delta x, the thickness, right? One surface times delta x. And so the area that I then have for this term and the area I pull out from here are going to cancel. And what I'll be left with over here then is just the delta x piece. And then I'm going to divide by delta x to bring it over to this side. So there's where this came from. Okay. So we've got, again, the flux at position x now, minus the flux at x plus delta x, and that's all over delta x. So just rearranging this, substituting v in. Okay. The other way I guess you could think about it, you're just going to take this, substitute it in, divide through by the whole area, the whole volume. So this would be a delta x, and then that a that was here will cancel out of both of those terms. All right, so there's my equation. Now, if you recall in calculus class, I guess maybe even pre-calc class, the definition of a derivative, the definition of a partial derivative, okay, df dx, is the function evaluated at a position x plus delta x minus the function evaluated at a position x. Right, so we just take the difference in the value of a function at some point and some point very close to it. And that's basically what this is saying. So f plus at x delta x, f at x. And we divide that by that difference delta x. And then we take the limit as this goes to 0. So basically these two values get closer and closer together. So this gives us a change in the function value, right, versus a distance. And that's our derivative, df dx. Well, that looks like what we have here. If we now, in the limit, let delta x go towards 0, so our volume element becomes very small. That's what we want to do. We basically have the definition here of the derivative function, the partial derivative function. The only difference is that our two terms are switched based on this. And so we'll have to throw a negative sign out here, and then we can flip these two terms. So we have the definition of a negative partial derivative. Okay, so dc dt then is equal to the partial derivative of the flux with respect to position. And there's the negative sign, again, to switch these two terms. So dc dt is equal to the negative of the flux with position. And this is referred to as the continuity equation. And this makes sure that we don't violate mass conservation. It's taking into account all of the mass. So the concentration that changes, the concentration change per time in a given location in our material is equal to the difference in the fluxes around that location. Okay, hopefully that makes sense. If our flux is constant everywhere in our solid, then the change in flux with position is 0, and then therefore dc dt is 0, and what that means is that our concentration is not changing at all in our solid. So we can have concentration differences in the solid, but they're not changing anymore. That's actually steady state. All right, so there's our continuity equation. So we're going to use that next time, and we're going to take the constitutive equation. So we'll recall what that is, and we're going to put it into this one and continue on in this problem. All right, so last time we found the continuity equation. So here it is again. Let me just remind you again of what this equation is saying. So we're looking at a volume element, a small piece of our membrane. And if we take a look at that small piece, we're saying that the concentration at that location changes with time according to the negative of how the flux changes with position. So if I'm looking at a given piece of material, I have flux that's coming into that location and I have flux that's leaving. right? So my flux could be changing with position. And if it is, then the difference in that flux will leave behind or take away mass. And so that'll result in a concentration change in that given volume element. Okay, and we looked at that last time. Right, so this term just represents, for example, a flux in minus a flux out. All right, so that's our continuity equation, takes into account conservation of mass. If there's no difference in the flux with position, then the flux in and the flux out would be equal, so there'd be no change in the concentration, right? This is 0, then our change in concentration with time is 0, and that would be steady state. All right, so now what we want to do is define the constitutive equation. And remember, the constitutive equation we mentioned last time, and we've got it defined also in your class textbook. This is the equation that governs the material behavior. Okay, and so we've seen things like Hooke's law, where we have a strain or a stress, say, applied to a given material, and that results in a strain, and what relates the two is the Young's modulus. Or maybe we change the temperature on a body, and the body changes dimension. It increases or decreases in length, depending upon whether that's a positive or negative change in temperature. And those two are related to the thermal expansion coefficient. These are all constitutive equations. Here we have a concentration difference over dc across the membrane dx. That has a thickness dx. And that change in concentration, that difference in concentration, results in a flux, the movement of mass across the film. And the constant that relates the two is the diffusivity. Okay? And then the negative sign here in Fick's first law takes into account the fact that the concentration gradient here needs to be downhill, a negative quantity, and then the flux would move in the positive x direction. So we get a positive flux for a downhill change in the concentration, right? And that just means that mass moves downhill from regions of high concentration to regions of low. And that hopefully makes sense. So what we want to do now in this step 3 is just simply take this constitutive equation. So this is the one we're going to use all the time in this first section doing mass. We'll have a different one, of course, in the heat and then fluids. We'll take this one and we'll stick it right in here into the continuity equation and then just rearrange a little bit. So I'm going to put it in. There it is. And then we get, through some rearrangement, Fick's second law. Now Fick's second law, as written like this, you can see that one of the things that we had to do is pull the d out of this derivative. Okay. Now the only way we're allowed to do that is if we state that we made an assumption here that this diffusivity did not depend on position. In other words, this is a constant. Okay, so the diffusivity constant, we can pull it out. Of course, the negative sign comes out, cancels with that one. And then we just simply have then the second derivative of the concentration with respect to x. Okay. Now this diffusivity equal constant is an assumption. It holds pretty good for a lot of cases, but not all cases. And if you take a look at the introduction video to the course, you'll see there that we looked at a case of carburization briefly, and I showed you the experimental data where the concentration was higher at the surface than it should have been by the model. And that model also assumed a constant diffusivity. And I pointed out there that, in fact, D, say for carbon and iron, actually changes with position because it depends on the concentration. So at the surface where the concentration was high, we had a higher value of D. So in those cases, I can't take this out of this differential. It needs to stay in here. Okay. And so that'll be a change at this step when you take a look at one of your homework problems where we're going to have a D that is no longer constant, but in fact depends on C. All right. But anyway, here is Fick's second law, and we'll tackle that other one when we get to it. So again, assumptions, we want to make sure that we do that. So we said that D is constant, that's in terms of fixed second law. And recall that we also used that A was constant when we derive this continuity equation. Okay, so far those are the two assumptions that we've made in order to end up here at fixed second law. So the next step, I'm going to do two steps in this video, is to go ahead and apply our experimental conditions. And in this case, what we're talking about is our steady state condition. So if this was not in steady state, then I would skip this step and I'd continue on. And we will do that, but those problems we're going to need to solve in Excel because they're time-dependent problems. They get much harder. Here we're going to use steady state conditions for a little while. So we're only interested in what happens in our sample, what is the steady state flux through the membrane, not what the initial flux is when we start up the process. So steady state, we talked about this, is the case where our variables are not changing with time. Okay? In this case, dc dt, that's our variable changing in time, is equal to 0. So steady state, we can't have anything changing in time. Okay? We can change things in position, so dc dx is not 0, but we can't change those concentrations at any given position when we look at the time element. So dc dt equals 0. So we let that equal to 0, and then we can divide both sides by d, so that disappears, and we end up simply with the second derivative of the concentration with position is equal to 0. All right, so these were partial derivatives in all of these equations, and they're partial derivatives because C depended upon, up to this point, two variables, x and t. Right? So this says we're going to hold the position constant, and we're going to take the derivative with respect to t. This one is looking at a given time held constant, and we're taking the derivative with respect to x. But now, since C doesn't change with t, then C is only a function of x, and therefore we don't need to be doing partial. We can do our ordinary differential. So d squared c dx squared. Okay, and now this is easy to solve by integration. So we'll go ahead and we'll take a look at that one